The second probability question has to deal with normal distribution probability and combining random variables. So it says each full carton of grade A eggs consists of one randomly selected cardboard container and 12 randomly selected eggs. The weights of such full cartons are approximately normally distributed with a mean of 840 grams and a standard deviation of 7.9 grams. Part A says, what is the probability that a randomly selected full carton of grade A eggs will weigh more than 850 grams? So as always with normal probability, the first thing we want to do is start with a z-score. So I know that my z-score is found by taking x minus the mean divided by the standard deviation. So if I take 850 as my x value minus a mean of 840, and divide by a standard deviation of 7.9, I will get my z-score. So I have a z-score of 1.266. And then I want to find the probability that z is greater than 1.266. So either you could look this up on your pink sheet, or I would recommend using your calculator as well. So on your calculator, if we go to second vars, normal CDF, my lower bound, since I want greater than 850 grams, would be that z-score of 1.266. Upper bound, a ridiculously large number. Mean of 0, standard deviation of 1. And I get a probability of 0.103. As always with probability, make sure that you're showing the formula, substituting the numbers in, and then calculating the probability. Also with normal distributions, you really need to show the work of calculating the z-score. Okay. So part B then says the weights of the empty cardboard containers have a mean of 20 grams and a standard deviation of 1.7 grams. So that's for our cardboard container. It is reasonable to assume independence between the weights of the empty cardboard container and the weights of the eggs. It is also reasonable to assume independence among the weights of the 12 eggs that are randomly selected for a full carton. So they say that let the random variable x be the weight of a single randomly selected grade A egg. We want to figure out what is the mean of the random variable x. Okay, so in order to do this, we're going to have to set up a little bit of an algebraic formula. So we know that with means, they follow the math. So the mean of the carton should equal the mean of the cardboard box or cardboard container plus 12 times the mean of one single egg. And that's what we're looking for, the mean of one single egg. So we know the mean of the entire carton is equal to 840 grams. The mean of the container they just told us was 20 grams, and we need to figure out the mean of an egg. So I'm going to pause the video, do my algebra, and then we'll talk through the rest. Okay, so I would say in this case, as long as you have the actual equation set up, you really don't necessarily need to show all of your work. The graders are not going to be looking to see that you can add, subtract, multiply, divide, simple computations like that. So I set up my equation 840 equals 20 plus 12 times the mean of an egg. I subtracted the 20, divided by 12, and then I got a mean of a single egg to be 68.33 grams. The next part asks us to find what is the standard deviation of egg, or one single randomly selected egg. So I'm going to take a moment to set up my equation and then talk to you about it. Okay, so if you recall from the previous question, or chapter 16 on combining random variables, we cannot actually add the standard deviation together of independent random variables. We can only add variances. So if you notice on the left-hand side, the standard deviation of the entire carton should be equal to the square root of the variance of the container plus the variance of each of those 12 individual eggs. Now, the other way I can write this is the standard deviation of the carton equals the square root of the variance of the container plus 12 times the variance of the egg. Well, if you recall, we're used to squaring our scale factors. So you might ask, okay, well, why aren't we squaring that 12? Well, in this case, we really are not scaling up the weight of those eggs or the standard deviation of those eggs. The eggs remain the same. We are just combining the variance of each of those 12 individual eggs, or continuously adding the variance of those eggs. That is why I do not square that scale factor. So again, I'm going to pause the video, add in my numbers, solve for the variance, and explain the rest of this. Okay, so if you look back to this step right here, I knew that the standard deviation of the entire carton was 7.9, and then the standard deviation of the container itself was 1.7. So I substituted those values both in. I then squared both sides to get rid of the square root to get 62.41 equals 1.7 squared plus 12 times the variance of egg. I then subtracted 1.7 squared from both sides, divided by 12, and then took the square root to actually get the standard deviation of 2.227 grams. So it's quite a bit of algebra for this problem. I would say a lot of this portion right here, you don't necessarily need to show all of that. Those steps that you're just doing in your calculator, you could probably omit.